There is a particularly unglamorous theorem in mathematics. If you put 5 pigeons into 4 boxes, then at least one box must contain at least 2 pigeons. The first time people hear it, they can hardly help laughing. It is something even an elementary school student can grasp at a glance. Yet it has a formal academic name, a rigorous mathematical proof, and a rightful place in mathematics textbooks around the world. More remarkably, countless problems that stumped leading scholars for decades have ultimately been cracked open by this very statement, which at first sounds almost tautological: the pigeonhole principle. The pigeonhole principle says that if we place n pigeons into m pigeonholes and n greater than m, then at least one pigeonhole must contain more than one pigeon. It does sound rather childish, doesn't it? So let me ask you a question. In a city of 5 million people, must there be 2 people with exactly the same number of hairs on their heads? The answer is yes, absolutely. And there is no need to count anyone's hair one by one. The pigeonhole principle settles it immediately. A normal person has no more than about 1 million hairs, so there are at most 1 million possible hair counts. Those are the 1 million pigeonholes. The city's 5 million residents are the 5 million pigeons. Since there are more pigeons than pigeonholes, at least 2 people must have the same number of hairs. No survey, no verification, no calculation. One sentence fixes the conclusion. If that sounds like nothing more than a daily life puzzle, the next 2 problems drawn from very different areas of mathematics reveal the real power of the principle. First, consider the classic chessboard puzzle. A standard 8x8 chessboard has 32 black squares and 32 white squares. Each domino covers exactly 1 black square and 1 white square, so 32 dominoes can cover the whole board. Now remove 2 opposite corner squares. The board has 62 squares left. Can the remaining board be tiled exactly with 31 dominoes? Intuitively, it seems plausible. 2 squares have been removed, so why should removing 1 domino make the board impossible to tile? But it is impossible without exception. The 2 opposite corners of a chessboard are always the same color. Once they are removed, the board has 30 squares of one color and 32 of the other. Yet every domino must cover 1 black and 1 white square. To place 31 dominoes, we would need 31 squares of each color. There are effectively 31 demands for squares of the scarcer color, but only 30 such squares available. By the pigeonhole principle, 1 domino cannot be matched with a distinct square of that color. Overlap would be unavoidable. There is no lucky arrangement and no clever workaround. One seemingly trivial observation eliminates every possible tiling. Now consider another problem. Mark any 5 points on the surface of the Earth. Must there always be a hemisphere containing at least 4 of them? Here, a hemisphere can be any half of the sphere obtained by cutting through the Earth's center, and points on the dividing circle count as belonging to both halves. Sounds like a geometry problem requiring complicated calculations, but the pigeonhole principle proves it in 3 sentences. Choose any 2 of the 5 points. Draw a great circle through those 2 points, and the Earth's center, dividing the globe into 2 hemispheres. The chosen 2 points lie on the boundary, and therefore belong to both hemispheres. The remaining 3 points must lie in one of the 2 hemispheres, 3 pigeons, 2 pigeonholes, so at least one hemisphere contains at least 2 of those 3 points. Add the 2 boundary points, and that hemisphere contains at least 4 points. No elaborate formula, no advanced derivation, just the same idea an elementary school student can understand. This point, you might say, these are just mathematical games. What do they have to do with real life? Consider a technology we use all the time: lossless data compression. Files and lossless image formats work by simplifying and encoding repeated information. For example, a line of black and white pixels might originally be written as 67 individual W's and B's. Compression software could instead represent 12 consecutive white pixels as 12W and 3 consecutive black pixels as 3B. What once took 67 characters might shrink to 18, while still being recoverable perfectly. Many people have imagined a universal lossless compression algorithm that could make every file smaller. Engineers have pursued versions of that dream for decades, but the pigeonhole principle rules it out completely. This is not a limitation of current technology, it is a mathematical impossibility. The logic is straightforward. Lossless compression has an absolute limit. Completely random data, with no redundancy at all, cannot be compressed without loss. Suppose an original file contains 100 binary digits, and we try to force every such file into an 80-bit compressed form. There are far more possible 100-bit files than 80-bit encodings. The original files are the pigeons, the compressed outputs are the pigeonholes. Since there are vastly more pigeons than pigeonholes, at least 2 different original files must be compressed into the same output. When it is time to decompress, the program has no way to know which original file to restore. The requirement of losslessness collapses immediately. No algorithm can evade this law. One simple principle closes the door on an entire class of possibilities. The chessboard puzzle, the points on the Earth, and data compression belong to fields that seem unrelated: geometry, topology, and computer science. Yet, all three are pierced by the same rule. One so simple, it almost seems laughable. That is one of the most beautiful things about mathematics. When a near common sense observation is distilled into a general model, it can sweep across apparently unrelated domains and give everyone who understands it that sudden, clarifying sense of course, that is why. And in life, the pigeonhole principle contains an even simpler lesson. We often want to optimize everything, fill every gap, and fit unlimited goals into limited time and energy. But the limits of our resources are real. There will always be more pigeons than pigeonholes. Accepting constraints, learning to choose, and recognizing that some kinds of perfection are impossible may be the clearest and most rational strategy of all.